Alright folks, in lesson 3 part B we are going to learn about the duality and sensitivity analysis. Okay, so first of all, what is the duality and why we need that? Okay, so one of the most important discoveries in early development of linear programming was the concept of duality. Every linear programming problem has an associated problem that called the dual. The original problem is known as the primal. These relationships prove useful in variety of ways. Okay, let's consider a maximization primal problem in a standard form. Okay, the dual will be a minimization problem, and dual uses the same parameters in different locations. Let's look at the primal problem. So we already saw this one, the standard form of a linear programming problem, whereas maximizing z equal to sum of c j xj subject to sum of aij xi xj less than equal to bi for I equal to 1 to m, where xj's are greater than equal to 0. That means non-negativity constraint. So when we convert this one into dual problem, what happens? This right hand side now becomes the coefficient of the objective function. Look at right here. Okay, so let's say we change it. First of all, we change to maximize to minimization. That's the first thing in the dual problem. We give a name w instead of z. Okay, we bring that bi in the top, and let's say that yi are basically new object decision variables. Okay, and what happens? These cj's are converted to the right hand side of the dual problem, where aij remains the same, okay, with new variable I. Okay, so I'm going to show you in a few minutes, and definitely yij is greater than equal to 0. And one more thing, you see that the constraint was less than equal to constraint, inequality constraint. It becomes greater than equal to inequality constraint. Okay, so this is basically the basic form of primal and dual relationship. One thing for sure, whether you maximize z or minimize w, both the result will be same. Okay, so the dual problem uses exactly the same parameters as the primal problem, but in different location. So in matrix notation, we can see the maximize z equal to cx, which will be converted to minimize w equal to yb for the dual problem, subject to ax less than equal to b. In dual problem, it will be subject to ya greater than equal to c, x greater than equal to 0, whereas y greater than equal to 0. Okay, where c and y are basically the row vectors, but b and c, x are the column vectors. Okay. So in relationship between the primal and dual problem, if we summarize that, what exactly happening? The constraint I now becomes the variable I. That means number of variable on the primal constraint, number of constraint in the primal problem will be now the number of variable on the dual problem. Okay, the objective function coefficients will be going to the right hand side of the constraint of the dual problem. Okay, so these variables, if it is a minimization, it will be maximization in the dual. If the variable is greater than equal to, it will be a constraint less than equal to. If the variable is less than equal to 0, it will be constraint equal to greater than equal to 0. If it is unrestricted, it will be equal to constraint equal to. Okay, and constraint will be variables. If the constraint is greater than equal to, it will be less than equal to 0 for the variables. If constraint is less than equal to, it will be greater than equal to 0 variables. If it is equal to, it will be unrestricted. Okay, all right. Next, let's go with an example. Now let's do a problem. Okay, so the primal problem that we have is maximize z equal to 3x1 plus 5x2, where x1 less than equal to 4, 2x2 less than equal to 12, 3x1 plus 2x2 less than equal to 18, and x1 and x2 are non-negative. So when we are going to convert this one to a dual problem, first of all, the maximization will change to minimization. Z will be w. You can choose any other symbol, but right now we are going to choose the w. We're going to go like that way. okay, equal to 4. Now how you get these new variable, how many you need? Basically the number of constraint that you have, you're going to add that many variable. So let me just do P. Okay, so in this case this will be say y1, this will be y2, this will be y3. Okay, these will be the coefficient of y1, coefficient of y2, coefficient of y3 for the objective function. Now when we are going to find the new constraint from here, how we are going to do that? This will be the constraint combining these two. Okay, the first constraint will be what? See that x1 is corresponding to y1, so that, and that coefficient is 1, so y1 right here, plus there is no y2 because this is 0, 3x1, so there will be 3y3, and as it is a less than equal to, all coefficient less than equal to, this will be greater than equal to 3. Okay, this 3 is coming from the objective function of primal problem. The second constraint will be addition of these two. So 2 is the constraint for y2, 2 is the coefficient for y2, 2 is the coefficient for y3, so 2y2 plus 2y3 greater than equal to 5. This 5 is coming right from here, and definitely all decision variable will be greater than equal to 0 as the primal one. Okay, alright. So in the matrix form, this is the way we're going to present that one, as we had z equal to 3, 5 times x1, x2. This is a row vector, this is a column vector. Okay, this is a1, 1, a1, 2, 2, a2, 3, x1 and x2. These are the right hand side, and x1 and x2 greater than equal to 0, which becomes now 3 variables with the 3 coefficients and so on and so forth. Okay, this is how you are going to write the matrix form of the primal and dual problem, which is exactly similar that we saw in the previous example. Okay, now the primal to dual table for the linear programming is like that way. So the primal problem, this is the coefficients, these are the coefficients. Dual problem, these are the coefficient of the variables. Right hand side becomes the primal problems cost coefficient, sorry, I should have said cost coefficient. G function coefficient will be the right hand side of the dual problem. Okay, and the right hand side of the objective function is basically it will be minimized objective function for the dual problem, which was the maximized for the primal problem. Okay, now the relationship between primal and dual problem. Remember one thing, the following relation is always maintained from the primal and dual. What happens? Y times ax must be less than or equal to yb. From the primal we know that ax less than or equal to b. Okay, so if you multiply y, this is exactly it look like. Or from dual, if we have this one, okay, so we just multiply the y, x in this particular case, which will be sign change greater than or equal to cx. Okay, for the weak duality, what happens? The cx will be always less than or equal to yax, which leads to less than or equal to yb. Okay, so this is basically weak duality, so it may or may not be the optimum for the primal, okay, solution. Whereas for the strong duality, everything should be same. That means you get the objective optimum solution should be the optimum solution for the dual problem as well as the right hand side. Okay, now there are complementary slackness conditions are obtained from the equation number 4. That means the previous equation right here. Okay, how we are going to obtain that? You just take these two equations first and move it on the left hand side, and you can find that one. And also take these two, y star ax star equal to y star b, where you can y star equal to times b minus ax star equal to 0. Okay, where xj star is greater than equal to 0, where y star aj equal to cj, or y star aj is greater than equal to cj, where xj star equal to 0. Okay, So you get the idea how we get the complementary slackness for this condition. So any pair of primal and dual problems can be converted to each other. The dual of the dual problem is always a primal problem. Just look at this right here. So this is a dual problem. So we convert it to the standard form. Okay, that means minimize, we make it maximize by taking negative sign on the both side, and the same thing for the constraints too. Okay, then this is basically, we can make a dual of this part, make it a minimization of minus z minus cx and so on and so forth. Then if we make it a maximization problem or convert to the standard form, so it will be maximize z equal to cx. So you can see that the dual of the dual basically nothing but the primal problem. Okay, so the another problem I basically want to share with you. See that in this particular one, minimize 0.4x1 plus 0.5x2, where we have 0.3x1 plus 0.1x2 less than equal to 2.7, 0.5x1 plus 0.5x2 equal to 6, 0.6x1 plus 0.4x2 greater than equal to 6, where x1 equal to greater than equal to 0, x2 greater than equal to 0. Look at that. This is the same problem when we actually introduced the operation research the first beginning. This is the problem we talked about the radiation therapy. Okay, now what happens? We have a less than equal to, we have an equality, another is a greater than equal to. So how we are going to deal with this one? So first of all, we are going to convert this one to the same inequalities. So first of all, what to do that, what we are going to do, we are going to take the negative sign on the both side to make it all greater than equal to. So the first constraint, this one, just so this one now becomes this one this way. Okay, now for the equality, what we are going to do, we are going to add two set of constraint, one with greater than equal to, one with less than equal to. So what happens exactly? So first greater than equal to becomes 0.5x1 plus 0.5x2 greater than equal to 6. That's one. Number two, 0.5x1 plus 0.5x2 less than equal to 6. So what exactly we did, as we have to make all the inequalities greater than equal to, so we take a negative sign on the both side like the first constraint and make it all greater than equal to. So exactly what is going on, let me just show you. If you have an equality constraint, we need to convert that like this way. So 0.5, just write it down, x1 plus 0.5 x2 greater than or equal to 6. That's one. Another one is 0.5 x1 plus 0.5 x2 less than equal to 6. So we already have the greater than equal to. To make the second one greater than equal to, we have to basically take a negative, multiply the negative one on the both side. Okay, and the last one will be remaining unchanged. So what happens now? We now have four variables. Number one, y1. Okay, number two, y2 plus. Number three, y2 minus. Okay, number four is y3. Okay, so these will be my new dual variables. So these will be my dual variables. Now if we write the dual problem, so what is going to happen? These will be my coefficients times these variables. If you go back, see that negative 2.7 y1 plus 6 y2 plus minus y2 minus plus 6 y3. Okay, and now if we want to write down the new constraint for the dual variable, it is nothing but these lines right here. You can see that, and these there. So there will be only two constraints, and they will be less than equal to 0.4 and 0.5 right here, and also the y1, y2 plus and minus and y3 will be greater than equal to 0. So if we basically put together everything. Okay, so this is the short form. We can find out that negative 2.7 y1 plus 6 y2, because y2 was replaced by y2 plus minus y2 minus, okay, and 6 y3 and so on and so forth. So in this case the y2 will be nothing but unrestricted, whereas the other two will be greater than or equal to 0. Okay, makes sense how you get the duality? Okay, then solving exactly the same way we did, we can use any software to do that again. All right, now we're going to talk about the sensitivity analysis. All right, for the sensitivity analysis in the linear programming is very important. Why is that? It basically gives us an idea how much can the objective function coefficient change before the values of the variable change. Okay, also how much can the right hand side of the constraint change if we obtain the different basic solution. Also, how much value is added or reduced to the objective function if I have a larger or a smaller quantity of a scarce resource. Let's do a problem. So suppose we have a problem called the Okoko problem, where maximize 20x1 plus 10x2 subject to x1 minus x2 less than or equal to 1, 3x1 plus x2 less than or equal to 7, with x1 and x2 non-negative. From here we basically got the solution. This is the solution basically we got, which is basically this point right here, okay, where x1 equal to 0, x2 equal to 7, and z equal to 70. Now the issue is how much can you change a cost coefficient without changing the solution. The cost coefficient means these two right here. Alright, that means if we denote that this is as C1 and this is as C2, so how much we can do that? To do this type of problem, what we need to really do, first we basically find the range of optimality, the interval associated with each coefficient, such that the optimum point remains unchanged. To find objective z equal to c1 x1 plus c2 x2, so the slope is basically minus c1 by c2. Okay, so there are three steps. One, find the slope of two constraints, define the optimal point, call these a1 and b. Okay, set a1 less than or equal to the slope of the objective function less than or equal to b. Okay, then set c2 equal to its original value and solve for c1. Again, set c1 equal to its original value and solve for c2. So for this one, let's take this previous problem and set c1, okay, right here. Okay, from here we can see this is basically my slope for the objective function. Okay, this is the slope for the constraint number 1, this is the slope for the constraint number 2. Okay, so we set at like that way. From here we can find c1 equal to negative 10 or c1 equal to 30, positive 30. Now if we have a negative number, that means we can basically decrease the value, c1 value, up to infinite. Okay, if we have a positive value, that means it can increase that much. That much means at the beginning we had what, 20. Okay, so we can increase 10 more. Okay, $10 or 10,000 more, whatever that unit is, to make the solution unchanged. Okay, similarly we can find c2, okay, where c2 is basically, now we put back c1 value from the original equation and solve for c2, and which gives us negative 20 and c2 equal to 6.66. so from there what we had at the beginning we had 10. Okay, so we can basically decrease the c2 value, 10 minus 6.66. okay, and then which basically gives you 3.33. Now let's interpret the same thing using the Excel solver as well as Lindo. Alright, so let's open that one first. Alright, let's open the Excel and set up all the constraint and objective function the way we basically did it. So at the beginning what we have the 20x1 10x2, where with the subject to x1 minus x2 less than equal to 1. I think yes. So let me fix that. Less than equal to 1, and 3x1 plus x2 less than equal to 7. Okay, so now let me make it bigger. So now if we basically use the solver, okay, in this case you see it's not the objective function exactly the same way we fixed it right there. Okay, if we solve it, okay, now we can see this solver solution that we have 0 and 7. If you go back to the slide, you're going to see that 0, 7, that was the objective function solution right there. Okay, the 70. So what we are going to do, we are going to add the sensitivity report right here and click OK. You can see the sensitivity report created on the left hand side corner called sensitivity report 1 for problem 1. If we open that one, see that what exactly it says. This is basically the final value of x1 and x2, 0 and 7. Okay, reduced cost is -10. Objective coefficient, this is the initial objective coefficient, it was 20 and 10, you know that. Allowable increase for x1 is 10. Remember what we get in our right here, what we get, 30. Remember that? Okay, so from there, that 20 minus 10 is 20 plus 10 is 30. So we can increase the coefficient 1 for x1 in the objective function up to 30. So it will not affect any changes. But we can decrease infinite number of number right here. You can see that right here, as we got the negative 20, I believe. Let me just check that. What is that? Negative 10? Yeah, so that is infinite. So we can decrease as long as we can. Let me show you what exactly I'm talking about. Okay, so let's say this is our solution, and for that one, for x2, this is my initial one, and we can basically decrease up to 3.33. Why increase and decrease change in the both way? Because the C2 and C1 is inversely proportional to each other. Okay, so we can see that the allowable increase on the previous one, if we go back to the purple side, we got the less than 20, my negative 20, which is infinite kind of, and C2, so this will be now increase and this will be basically decrease, as I mentioned earlier. So you got 3.33 if you subtract 6.66 from 10. Okay, so let's go back right here. Okay, let's go to the problem 1. Alright, let's set this to the original value. Okay, let's change this one to 30. Say 30. Okay, yes. Alright, so we are going to increase that 10. So let's see what happens if we click on the solver. Okay, exactly the same thing. We are not doing anything. If we solve that, what happened? See that the solution didn't change, but the value, optimum value of x1 and x2 changed. Okay, so we basically got a different point of the feasible space, our new solution. Okay, let me cancel that, so it will revert back to previous one. So if we decrease this one, say 10, some 20 to 10. Okay, what happens now if we do the solver again? Let me click the solver. See that it really didn't affect. Okay, so this is basically the thing we're talking about. Now let's go back to the sensitivity analysis report. Right here, the shadow price. What exactly the shadow price means? This is basically the dual variable value of the primal one. In Excel, it will come up as a shadow price, which is nothing but the dual variable values right here. Okay, which means that if we increase the right hand side of the constraint, this is basically the second constraint, I believe. Okay, so if we increase right hand side with at least 1, you can see allowable increase infinite right there, at least 1, we are going to get each increase, we are going to add 10 more improvement in our cost function. Okay, that means our optimum solution will increase by 10. Okay, let me just show you what exactly I'm talking about. Say I'm going to increase the 7 to 8 as allowable increase is infinite. Okay, now if I solve this one, okay, let me just look and solve it. See that how much it increased? Exactly 80. Okay, there's 10 for one increase on the right hand side of the second constraint. We got 80. Optimum solution becomes 80. All right, let me just leave it like that. Now let me use the same thing in Lindo. Okay, so what we can do in this case, let me just bring it right here. Okay, 1 second. All right, you can see that right here we have the same maximize 20x1 plus 10x2 and so on and so forth. Okay, and if we basically solve this one with the sensitivity analysis with our problem, see what happens in the dual variable right here, the dual prices. This is exactly the same, 0 and 10. Okay, which was basically shadow prices on the previous one. Objective say optimum value is 70, x1 0, x2 7, and the increase of x1 can be up to 10. That means 20 plus 30. That means you can increase this 20 up to 30. Okay, if you go back beyond 30, everything will change. The optimum solution will not be the same anymore. Okay, for x2 it doesn't affect because we do not have anything on the optimum value right there. You can see that. Okay, so this is how you read through the sensitivity analysis. Okay, so that's basically allowable decrease, allowable increase. So if we have a question like that, how much you can suppose we are going to increase the cost coefficient up to 30 for the x2, what will be the effect? So you have to answer this type of question. Or if we ask that if we increase the right hand side of the constraint 1 by 2, what will be the solution, what will be the effect on the optimum solution? This type of question. Okay, all right, let's get back to the PowerPoint again. All right, so now suppose what if we invest 2 only pays 5,000 per share. Okay, so instead of 20, now as 10 we change it to 5. Now the optimum solution is now in the point 2 and 1. The issue is at what value of C2 does the solution change. So basically we need to find out the highest range of C2 that will change the solution. That means at again the issue is at what value of C2 does solution change. So in this case we are going to basically solve for C2 now, exactly the same way we did previously, and we see C2 is basically 6.67. okay, that means what? This is basically the new solution. Okay, so this will be basically our new objective function. So if the C2 goes beyond 6.67, okay, we have to basically the solution will change. Next, so this is exactly same thing that I showed you on Lindo. Okay, so now what happens? What if we only 5 hours available at the time constraint? Okay, so instead of 7 we have 5. Now the new constraint becomes like that. Okay, so what exactly happens? The optimum solution is now 0.5 and 0, but the basis does not change. So at what value of right hand side does the basis change? So what happens right here? The basis change at this constraint. Okay, so we need to find out what will be the non-basic for the x2. Okay, so when the constraint is 3x1 plus 2x2 less than or equal to 0, then x2 becomes the non-basic, and then the basis will change. Okay, so this is how you do the sensitivity analysis for this one. You can see that right here. As we mentioned earlier, this is exactly the same thing, same problem, same idea. Okay, and so it will be basically reduced by this much or increased by that much. This is the dual price right here. Okay, you can see that. So now next is how much are you willing to pay for one additional unit for a limited resource. Okay, say we have the same thing as I actually showed it to you. If I basically add one unit, what changes that makes? So it will change up to $10,000. Okay, as it is $10,000 per unit. Okay, so from the dual prices or reduced cost, okay, from the dual prices, that, or the shadow price in Excel, that gives you the idea whether how much it will increase or decrease, like that. Okay, right. So next, this is exactly the same thing. Now, what if more than one coefficient is changed? Okay, so that means 100% rule for objective function coefficient. If sum of coefficient changes divided by coefficient original coefficient changes less than equal to 1, then the optimum solution will not change. Where del C is the actual increase or decrease, del C is the maximum allowable increase or decrease on the sensitivity analysis. Let's do another problem. Okay, for this particular one, let's take that and put it in. Let me solve that problem in Excel first. So we've set up this whole thing. Okay, where we can basically see there. Just okay. So this is the Excel function. You can see that this is 5 and 6, 2 and 1, 2 and 3, then 120 and 240. You can see 120 and 240. Okay, set up the objective function exactly the same way. Click on the solver. Okay, this is a maximization function to okay, so this is maximize. If you click solve and ask the sensitivity analysis, this is the report. You can see that right here. Okay, so allowable increase for the cost coefficient, okay, is basically you can go up to 12. So 5 plus 7, 12. And allowable increase for coefficient 2, that means C2, will be 6 plus 1.5, that means 7.5. And the similar way the decrease, so you can go below, cannot go below 4, or you cannot go below 2.5. Okay, then the solution will change. On the other hand, if you increase, this is basically dual variable value. Okay, so if you increase the right hand side, the first constant right hand side, okay, up to you can increase up to 240, so 120 plus 120, okay, and you can decrease up to 80, okay, but per increase your objective function will improve 0.75 for the if you increase 0.75 will increase. Okay, if you increase the second constraint by 1 unit, your price will increase 1.75. Okay, let me just do that. Okay, let me just go right here and increase, say, 121. Okay, and this is let's do one at a time. So now let's set back to zeros again. Okay, so what we are going to do again, click on the solver, solve. See that in this case what happened? It increased 0.75 because we increased the right hand side for the first constraint. Now let's go back to the zeros, and if we increase the both, let's say what happens. Let's say 241. Okay, so if we do the solver again, solve, see that it has 512.5. How you get that? If you go back to sensitivity report, so for 1 unit increase on the right hand side of constraint 1 will increase 0.75. For 1 unit increase of constraint 2, it will increase 1.75. So 0.75, 1.75 basically gives you what? 250. Okay, so if you go back to the problem 2, see that 510 was your previous answer. When you increase by 1 unit, they both increase exactly the value that showed in the sensitivity analysis. Okay, so you can do that exactly the same thing in Lindo. Okay, let me just delete that. Okay, so this is basically the way we set up the equation. Let me fix it. This is basically for plus, not minus. Look here, I did it correctly. 2, 1, 2, 3. Okay, now if we go for the solution and ask for the sensitivity analysis right here, see that this dual price, which is the shadow price, if you increase 1 unit of the constant 1, it will increase 0.75. 1 unit on the right hand side for constant 2, it will increase 1.75 the cost. Okay, similarly they say exactly the same value that we got in Excel that has been produced in Lindo too. So we can use the same thing in Lingo. Let me just show you one quickly. Okay, so in this case I'm going to type it in make max equal to that times end it with the, just delete this. Okay, with the semicolon. This one is make it commented one, and it with the semicolon, multiplication. All right, everything set up for the Lingo. If we click solve, see exactly what we get. Okay, let me just do that. Okay, so this is basically the solution. Let me put it horizontal. That'll be easier. Okay, so you can see that the dual price is given right here. This is my objective function right there. Okay, so now to see the range or the sensitivity analysis, what we need to do, we need to go to the solver. Click right here, solver, click range. Okay, that is basically your sensitivity analysis right here. Allowable decrease, allowable increase, and so on and so forth. Okay, exactly the same way you can do it in Lingo, because if you cannot install Lindo in Mac, okay, if you have a Mac, just an FYI. Alright, let's go back to the PowerPoint. Okay, so the simultaneous, I already show you this thing by default. Okay, so 100% rule, what exactly say on the right hand side, if this condition set is less than equal to 1, the optimal basis product mix will not change. That means optimum solution will not change, where del beta j is the actual increase or decrease of the coefficient. Del beta j is the maximum allowable increase and decrease on the from the sensitivity analysis. Okay, that's it for the sensitivity analysis. I'm going to post few problem for you to solve, and I'm going to add the goal programming tomorrow. Okay, so that'll be your lesson number 4 on the goal programming. Okay, so this is basically ends lesson number 3.